Hello everyone, here's another video on circular motion, lesson 4. We're going to talk about minimum speed and banked corners. Let's kick things off with minimum speed. Normally this would be associated with some sort of loop-the-loop situation. Of course, roller coasters are a good example of this. And it's going to be referring to the moment at which the object is at the very top of the loop. And you can imagine if the speed of the cart or the tram coming in is such that it is just slow enough such that at the very top of the motion, the contact between the track and the object becomes so minimal that in fact there is no contact essentially. Let's rephrase that. There's contact, the track is touching the car, but there's no force. Okay, you have to imagine this perfect scenario so that the only force then acting on the cart is the downward force of gravity. Okay, in other words, this force that we would normally associate with an Fn, this force is gone. It's the speed of the car in the circle is such that that force becomes zero. So let's do a quick analysis on this then. So we've just stated that the only force now acting on this object at its minimum speed, the minimum speed required for it to still be in contact with the track here, but not falling out of it. Okay, the minimum speed is going to be when the Fn is equal to 0. So this makes our Fnet expression really quite easy. We would go ahead and say that in obviously the y component, the up and down component, we are dealing with circular motion, and so the sum of all forces is the centripetal force, and that is only going to be Fg. That's the only force acting to the middle. Now we're going to say the middle of the circle is positive, the outer side of the circle is negative. That means I can have a positive centripetal force, and my gravity is also positive, so that's going to be mg. Now we're dealing with speed, so we would go ahead and say v squared m over the radius of the circle is equal to the mass times gravity. Of course, that means that the masses cancel out. That means that the masses don't affect any of the kinematics or the dynamics in this scenario. And so then we're left with an equation for the minimum speed such that it is gr square rooted. And that's our equation for the minimum speed required for the car to still remain in contact with the track and not fall out of the circular motion, but where the Fn is 0. So this is the minimum speed. Okay, the second scenario in our circular motion situations could be a banked corner. And you can imagine a racetrack whereby cars zoom around and the engineers of the racetrack have built it in such a way that the corner is banked. Here's a picture of the famous Daytona racetrack, and you can see here that the corner itself is at an angle. So if we were looking at this yellow car here, there would be an angle like this, and of course we would make our angle relevant to the horizontal. So this would represent the x, this would represent the y, and we would be dealing with an angle like this. So let's go ahead and draw a little simplified version of this. The good news is, to start with, we're going to treat the situation such that the coefficient of friction is 0. In other words, there is no friction. That makes our analysis a little bit more straightforward to begin with. And then later on, I'll probably make a separate video about friction and how that can be a factor. So yeah, let's do a little analysis here then. We're going to just shrink this down just to get that out of the way. And we can now think of a situation, something like this, where now we've got a cross section of the car. This is car is coming towards us. We might have the center of the circle here. So then we could obviously say that this going from the car to the center of the circle, that would be the radius of the curvature. But most importantly now we're going to think of the forces acting on this car as it goes round a circle on a banked corner. So right away we want to think about obviously gravity here. This is Fg. We're going to put the angle in, so that's the angle of the banked corner. And it turns out that if you keep analysing your triangles, you could get a triangle. Let me just move Fg out the way. Here we go. We could keep analysing this triangle. I'll use green here. Like this, making a triangle here with a little right angle. Obviously, this is still Fg. This angle in here would be the same. So let's call this green theta. So we're going to say that green theta is equal to the theta of the banked corner. Okay, and now we're going to go ahead and think that, well, if the car's on a banked surface and we want to think about the force normal, that's going to be perpendicular to the surface. So this here is the force normal. And that force normal is going to have a component that goes in this direction. Okay, and it's also going to have a component that goes in this direction. Okay, now this is where we start thinking about the x and the y in slightly different terms. So let's think about the y direction first, the up and down direction. So if we think about the car is going around a circle. At this moment in time, it's coming straight towards us out of the page, but it's going in a circle. So we would say, based on our understandings of circular motion, we would say that there is an acceleration here. This yellow dotted line is the centripetal acceleration to the center of the circle. But in terms of up and down, it's not going up or down. We're going to say that it's in a fixed point. That gives us this fixed radius. And so it neither accelerates through the tarmac or jumps up into the air. There's no up and down motion whatsoever. There's no up and down acceleration whatsoever. So we're going to say in the y direction that the F net is equal to 0. And that allows me to make the statement that the Fg value is going to be equal to this red arrow over here. Okay, and that's important because now I can make a statement about that red arrow. First of all, noticing that these angles, if this is the red theta, that's also equal to the green theta, which is also equal to the black theta. So I'm going to make a statement about that, that red component there. And of course, you can see this, I'm sure, since this red component is adjacent to the hypotenuse, which is the Fn, we can say that this is Fn cosine theta. In other words, Fg is equal to Fn cosine theta. Okay, that's our y analysis done. Let's look at our x analysis, and hopefully you can see now that the F net is going to be equal to the centripetal motion. Again, these are our two physics principles that we've stated from the beginning in the different dimensions. So again, in the horizontal dimension, we're going to be talking about the centripetal forces. Now, what is acting in the centripetal direction, the center-seeking direction? Because we're looking for this acceleration force. Well, again, take a look at our red triangle. You can see that the Fn has a component in the horizontal direction. So let's go ahead and call that out. That's going to be Fn sine theta. Okay, that's the arrow right here. And that can be now added to our x analysis. So Fn sine theta. So now we do something really cool. We look at these two equations and we say, well, what do they have in common? And what can we then use between the two? Well, hopefully you can see that both of these equations have Fn in common. So what we're going to do is take the y equation and solve it for Fn. So that would be mg Fn cosine theta. and that would give us Fn being equal to mg over cosine theta. We can then take this little equation and replace it with the Fn in the x statement. So let's go ahead and do that. So we're going to say Fc is equal to mg over cosine theta. That's the replacement there, multiplied by sine theta. All right, that's kind of neat. Well, the other thing we might know from math is that tan theta is equal to sine theta over cosine theta. This means that we can now insert tan theta into this part of the equation. So let's just move, let's just go ahead and write it. Let's see if we can squeeze it in here. We're going to say that Fc is equal to mg tan theta. And so now we can make our final statement about the speed going around here using this condition, because of course I can say that v squared m over r is equal to mg tan theta. Now again, once again in circular motion, the masses cancel out, and I'm left with the speed required to maintain circular motion when there's no friction in a banked corner is going to be v is g tan theta r square rooted. And that equation would give us the speed that we'd need to stay in that banked corner. So now we're ready to look at a sample question. So we have a velodrome cycling track, and it's got a maximum banking angle of 42 degrees. We need to show the the acceleration of the cyclist in this situation with no friction. So that's the scenario that we've just described. No friction, of course, meaning that mu is 0. Velodrome tracks, much like any other banked corner, look kind of like this, and we would have a little diagram just to represent that over here. We would go through, normally I would expect you to go through and do all the analysis, so you'd be putting on all your forces as we did before, so don't miss that step. So you've got your Fg, you would have your Fn, you would have, let me just move this out of the way, you would have the components of that Fn, which would be here and here. So let's go label this. That's not Fg, that's Fn. Fg's down the bottom right here. Now we would represent the angle here. Let's say that's 42, which means that is also 42. Put that in there. And the two components here are Fn cosine theta, that's this component here, and Fn sine theta, that's the component at the top. So in our x analysis, we would say that we have centripetal forces being, well, let's just start with the F net. The F net is the centripetal forces, and therefore the centripetal forces are going to give us the center seeking, which is this way. This is the acceleration centripetal, and that's going to be equal to the Fn sine theta. In the y, the up and down analysis, we have this equilibrium statement, 0, because it's neither going up nor down, and that means that the Fg is equal to the Fn cosine theta. Okay, so this would be mg is Fn cosine theta, and then if we solve for Fn, we get mg over cosine theta. Of course, over here, we would be saying that acceleration centripetal times the mass is going to be equal to, and this is where we add in the Fn equation here. We're going to substitute that in, so we would get mg g over cosine theta times sine theta. We also know that sine theta over cosine theta is tan theta. So we once again substitute this into here, and we would have a statement that is the acceleration centripetal times the mass is equal to the mass times gravity times tan theta. The masses cancel, so when we're asked to find the maximum centripetal acceleration at this angle with no friction, we would say that it is g tan theta. And if you plug that into your calculator, you're going to get a value of 8.8. And I've only got two significant figures, so that's I have to give my answer to two significant figures, so 8.8, and that is, of course, meters per second squared.